Hello and welcome back to another lesson on A-level physics. Today's learning intention is to explain how objects reach terminal velocity. The success criteria for today is to be able to explain the factors that affect drag force and to be able to explain why terminal velocity exists. Let's consider what is meant by a fluid. First of all, a fluid is either a liquid or a gas. Now, any object which moves through a fluid experiences a drag force as shown in the diagram. The direction of the drag force will be in the opposite direction to which the object is moving. Now, the size of the drag force depends on many factors which include the shape of the object, the speed of the object, and the viscosity of the fluid. If you haven't encountered the word viscosity before, it essentially means how thick or dense or gloopy, if you like, the fluid actually is. So things like oil would have a higher viscosity than water. Now we're going to look back at an example that we will have done before in GCSE physics, which is a skydiver who has just jumped out of an aeroplane. When a skydiver initially jumps from a plane, his weight causes him to accelerate because initially there will be no drag force acting on the skydiver. The only force on him will be the weight which acts downwards. Because he accelerates, his speed will increase, and so therefore the size of the drag force will also increase. The drag force is actually proportional to the velocity of the skydiver squared at high speeds at least. The velocity of the skydiver will increase, but becomes a constant when the forces acting on him are balanced. The free body diagram shown here on the right hand side of the board shows the forces that act on the skydiver, with the weight acting downwards and the drag force acting upwards. Obviously you can use the word air resistance instead. The resultant force acting on the skydiver is therefore going to be the weight minus the drag force, because the weight is going to be the larger force until we reach terminal velocity. When they balance out, the resultant force is zero, so he is no longer accelerating, and therefore we say that the skydiver has reached terminal velocity. When the skydiver eventually opens the parachute though, the surface area is going to dramatically increase, and that will cause the drag force to increase as well. That means that the drag force is now going to be greater than the weight, and so the resultant force acting upon the skydiver will be upwards despite the fact that it's actually moving downwards. That is going to cause the skydiver to decelerate. As he decelerates, his speed is going to reduce, and so therefore the drag force acting on him will reduce also. Eventually his weight and drag force will balance again, so that the resultant force acting on him is zero and there is no acceleration. He is now going to be travelling at a slower terminal velocity. This shows what the velocity time graph would look like for a skydiver. As you can see, the velocity is increasing until it reaches a constant velocity. In this example, the constant velocity is 60 meters per second, which will be the terminal velocity. Do please notice that that line isn't a straight line either. It is a curved line as the velocity increases, because the size of the drag force acting on him is increasing, and so his acceleration reduces. Once the parachute opens, the terminal velocity shoots down essentially to a much slower speed, and then he falls again at a constant speed. Okay, on the next couple of slides are going to be some exam questions. We will read through them. I'd like you to then pause the video and have a go at the questions before looking at what the answers are. So the first exam question says, Figure 4 shows the variation with velocity v with time t for a Formula 1 car during a test drive along a straight horizontal track. The total mass of the car and the driver is 640 kilograms. The car engine provides a constant driving force of 5,800 newtons. And the first thing that we've been asked to do for 3 marks is to determine the distance travelled by the car in the first 10 seconds. Have a think about how you do this question, pause the video, and then we'll go over the answers. So, to determine the distance travelled from a velocity time graph, we need to work out the area underneath the graph. Now, the issue here is that over that first 10-second period, we haven't got a straight line, it's actually slightly curved. So it's not quite as straightforward as working out the area of a triangle, although that would give you a crude estimation. Now, you'll get your first mark for simply stating that you are trying to work out the area under the curve, or as long as there's evidence that that is what you've tried to do. Now, we need to be able to work out the area under the curve, and we will do that by estimating the number of squares underneath it. If I was doing this in the exam myself, I would very lightly in pencil draw some squares on like so. I'd do it quite quickly obviously and count how many squares we've got. As you can see from my drawing there, we've got 19 full squares, but we also have part of a square here, part of a square here, 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 here and here. I don't think it will be too much to guesstimate then that there's actually going to be 22 whole squares here, because if there's 19 full ones, then here these would make 20, those two might make 22 and 21, sorry, and those two might make 22 in total. So we'll guesstimate that there's 22 large squares. Now we'll then work out what the area of one of those large squares is going to be, and as you can see from the axes, 2 seconds across and 10 meters per second up means that the area of one square will be 2 times 20, which is 20 meters. So because there are 22 squares, we do 22 multiplied by 20, which gives us 440 meters. Now obviously, depending on how you have drawn your squares and how accurate you've wanted to be, there is going to be a range of different answers available. The mark scheme for this exam question said accept any answer between 425 metres and 450 metres. Part B. Show that the instantaneous acceleration is about 4 meters per second squared when t is 10 seconds. Now, instantaneous means at that exact moment in time. So it means what is the acceleration, or show that the acceleration is 4 meters per second at exactly 10 seconds. Now, as you know, acceleration is the gradient of a velocity time graph. But to work out this gradient, we need to draw a tangent line because it is not a straight line. So I've drawn there for you on the board a tangent line at 10 seconds, and I will then want to work out what the gradient of that tangent line is by doing the change in y divided by the change in x. I'm going to use my entire line that I have drawn, and I have gone back through a vertical height of 60 meters per second, and the time across is 15.2 seconds. So 60 divided by 15.2 gives me 3.9 meters per second squared, which is of course 4 meters per second squared. Close enough. Now the mark scheme, it says to accept any answer between 3.6 and 4.4 meters per second squared, depending of course on the variations in your tangent lines. Part C. Calculate the magnitude of the resistive forces on the car when t is 10 seconds. Now, we know quite a lot of information. We know what the size of the driving force is, we know what the mass of the car is, and we've worked out the distance travelled and the acceleration at 10 seconds. So, to work out the resultant force, we use F equals ma, and that gives us a resultant force acting on the car of 2,496 newtons. But let's consider what the actual forces are. We'd have the engine force going forwards and the resistive force going backwards, and so the engine force minus the resistive force will be equal to 2,496. So, when we substitute all the numbers in that we know, the engine force is 5,800, subtracted the resistive force is 2,496. So rearranging that equation will give us a resistive force of 3,304 newtons. Part D. Calculate the power in kilowatts of the car at maximum speed during the test drive. Now, obviously, we'll have the maximum speed read off from that graph. Now, you've got to read off carefully because it actually reads off as 89 meters per second. We will then use the equation power equals force times velocity, which is on the A-level formula sheet, to do the driving force, which is 5,800, multiplied by that velocity, which is 89, which gives us 516,200 watts. However, it wants the answer in kilowatts, so we need to divide that by 1,000 to give us 516.2 kilowatts, or simply 516. Part E. The diagram shows the aerofoil that is fitted to a Formula 1 car to increase its speed around corners. However, the aerofoil exerts an unwanted drag force on the car when it is travelling in a straight line, so a drag reduction system, or DRS, is fitted. This system enables the driver to change the angle of the aerofoil to reduce the drag. The graph shown to you in part A, which we looked at earlier, is for a test drive along a straight horizontal track. Under the conditions for this test drive, the DRS was not in use and the engine produced a constant driving force. Explain why the velocity varies in the way shown by the graph, and then go on to explain how the graph will be different when the DRS is in use and the driving force is the same. So, to break that down then, there's two parts to the question, the last two paragraphs there. We'll start off by explaining why the velocity varies in the way shown by the graph. Now, it is definitely worth pointing out to begin with that the velocity increases or the car is accelerating because the driving force is larger than the drag force on the car, or there is a non-zero resultant force. We can also point out that the drag force is going to be 0 at the start, and we can also say that the drag force will increase as the velocity increases because the drag force is proportional to the velocity or the speed squared. Now obviously to say that, that only applies at certain speeds, so when you're considering very small amounts of movement we wouldn't be able to say that, but for speeds of motor cars we can definitely say that drag force is proportional to speed squared. The terminal velocity is going to be reached when the resultant force is 0. That will also get us the mark. Now we then need to answer the second part of the question, which was go on to explain how the graph will be different when the drag reduction system is in use. So when the drag reduction system is in use, that means that the drag force is going to be less for a longer period of time. But that means that the acceleration initially would actually be the same for the car because it starts with 0 drag force. With or without the DRS, we would actually have the same initial acceleration, and so the gradient of the graph at the beginning will be the same. We can then point out that we would actually reach a higher terminal velocity, and that is because we've been accelerating over a longer period of time. Now obviously there's more than 6 marks available there on the board, but any 6 of those will get you full marks on this exam question. Let's now have a look at a second exam question then. So this one says a steel ball has a diameter of 2.2 times 10 to the minus 2 metres, and we've been asked to calculate the weight of the steel ball, give your answer to an appropriate number of significant figures, and we've been given the density of steel as well. Now, to do this then, we know that a ball is going to be spherical in shape, and so we can use the equation on the formula sheet for working out the volume of a sphere, which is 4/3 pi r cubed. When we substitute in the values for this ball, the radius of the ball is going to be 1.1 times 10 to the minus 2, because obviously radius is half of the diameter, and so that means that the volume should come out as 5.575 times 10 to the minus 6 metres cubed. We can then work out what the mass of the ball is going to be because we know the density of the steel and we know the volume of the ball. So mass being density times volume gives us a mass of 0.0451 kilograms. We can now simply work out the weight because weight is mass times gravitational field strength. So we would do 0.0451 times by 9.81, which gives us 0.443 newtons. However, that will not get us full marks because it says in the question that we need to give our answer to an appropriate number of significant figures. Now, all of the data in this question has been given to 2 significant figures because we were told that the diameter is 2.2 times 10 to the minus 2 and the density of steel was 8,100. So we give 0.443 to 2 significant figures, which is simply 0.44 newtons. Part B. The diagram shows 2 identical steel balls dropped from rest into containers of oil. Now what you can see from that diagram is that steel ball A enters the oil immediately, whereas steel ball B is allowed to fall in air before entering the oil. It then says the graph below shows the velocity for steel ball A against time. And for 6 marks, we've been asked to explain the shape of the graph. Your account should include how the velocity and the acceleration of the ball vary with time, and a reference to how Newton's first and second laws of motion apply in this situation. I've marked this question quite a few times, and what is confusing to students about this is that they feel the need to actually quote Newton's first and second laws of motion in this, and you don't. As long as you are talking about with the direction in which forces are acting and the resultant force and what happens to it, that is reference to Newton's first and second laws. So let's start off though with saying how the velocity and the acceleration vary with time. Well, clearly the velocity is going to increase because the weight is larger than the drag force. Now that is a reference to Newton's second law straight away. We can then say again that the drag force is going to be 0 at the start, and then we can go on to say that initially the gradient of the graph is going to be equal to 9.81 meters per second squared, because it obviously falls freely to begin with. So the gradient of the graph is equal to the acceleration, and so it will be 9.81 meters per second squared at the beginning. The drag force increases, obviously because it's falling through oil, and so as the velocity increases, the drag force does, because drag is proportional to velocity squared. The resultant force is going to be the weight minus the drag force. And then the final mark is saying that we reach terminal velocity when the resultant force is equal to 0, because the weight is equal to the drag force. Final question. On the axis below, sketch the velocity time graph that you would expect to see for ball B. Assume that air resistance is negligible. Now that statement about air resistance is essential, because if we were taking air resistance into account, you might argue that the ball might reach terminal velocity before it hits the oil, and so therefore the line would be curved initially as it is for ball A. However, because we are assuming that air resistance is negligible, we'd actually see the velocity increase linearly up to the point when it hits the oil surface. Once it's in the oil surface, the velocity is going to be reduced until it reaches a terminal velocity, and then obviously it's going to stop when it hits the bottom of the container. Now the 3 marks are as follows. 1 mark for a straight line in the first section, like what I've drawn there. The second mark is for any descending line in the second section, so it could be straight, but the 3rd mark is for correctly doing it in the second section as a curve, and there be no incorrect continuation beyond the second dotted line. I hope you found these exam questions straightforward. If you have any questions, please leave one in the comments.